In question 1, we have to determine the relative growth rate. That is, we have to determine the value of k. So for this, I'm going to use the generic population model, that is, which is represented as P of t. This equals P naught e raised to the power of kt, where this P of t is the population of the bacteria after t hours. This is represents the population after t hours, and P naught represents the initial population of the bacteria, or we say that initial count of bacteria. K is the growth rate. This is what we have to determine, and T is the time in hours. We are also given the information, that is at T equal to 2, that is after 2 hours, the population or the count of the bacteria is 400, and after t equal to 6, that is after 6 hours, the bacteria count is 15,625. So we are going to use this model and as well as use the given information. So let me first copy the model once again, that is P of t, this equals P naught e raised to the power of kt. So I'm going to plug in this information in the first row, that is when t equals 2, the population or the count of the bacteria is 400, and this means P of 2 equals 400. So let's plug T equal to 2 into this model. When we do that, we get P of 2, this equals P naught e raised to the power of k times of t is replaced as 2. So this is how it becomes. And since we know that P of 2 equals 400, this can be replaced as 400. So therefore, we have the equation 400 equals P naught e raised to the power of k times 2 is 2k. So let's say this is equation number 1. Now I'm going to use the second information, that is in the second row. That is when t equal to 6, the population is 15,625. So we say that when t equal to 6, the population or the count which is represented as P of 6, and this equals 15,625. So once again, we can plug in this information into the population model. So when we do that, we first replace t by 6. So therefore, this becomes P of 6 equals P naught e raised to the power of k times of 6. We know that P of 6 equals 15,625. So I'm going to replace this quantity by 15,625, and this equals P naught e raised to the power of k times of 6 is 6k. Let's say this equation as number 2. Now we got two equations in certain variables like P naught as well as k. We have to determine the value of k. So I'm going to do this operation, that is I take this equation 2 and divide by equation number 1. So when I do that, I have to divide the left side by the left sides and the right side expression by the right sides. So into the left side, the quantity or the expression is 15,625 divided by the left side quantity in equation 1 is 400. So I have to divide by 400. And this side, on the right side, we have for equation 2, we have P naught e raised to the power of 6k, and so this is divided by the right side of equation 1, which is P naught e raised to the power of 2k. We will now simplify this and determine the value of k. So we can plug this into the calculator, that is 15,625 divided by 400, and this gives 39.0625. And this equals, we see that we can cancel this P naughts, and we can simplify this e raised to the power of 6k divided by e raised to the power of 2k using the power rule or the law of exponents. That is, this powers will get subtracted. This 2k will be subtracted from 6k. So that is 6k minus of 2k, which is 4k. It is e raised to the power of 4k. So I can write down this as e raised to the power of 4k. Now to determine the value of k, I'm going to take natural logarithm to both sides. So let me take natural logarithm to both sides. When I do that, this will be natural logarithm of 39.0625, and this equals natural logarithm of e raised to the power of 4k. And I'm going to use the power rule of natural logarithm. When I do that, this power comes in front. So therefore, in the next step, I can rewrite this as 4k times of natural logarithm of e. And it is known that the natural logarithm of e, the value of natural logarithm of e equals 1. So therefore, we can simply replace this quantity by 1, or we can just remove it, because 1 times of any quantity is the same quantity. So on the right side, we have only 4k, and on the left side, we have natural logarithm of 39.0625. And this equation helps us to determine the value of k if we divide both sides by 4. So therefore, k equals natural logarithm of 39.0625 over 4, which we can plug this into the calculator. And when we do that, we get the approximate value of k equal to, so this is approximately 0.9163. And I have rounded this to 4 decimal places. So we say that the k is approximately equal to 0.9163. Let's answer question 2. Here we have to determine the initial size of the culture, that is, we have to determine P naught. Since we have already determined the value of k, which is approximately 0.9163, we can plug the value of k into any one of the equation, either into equation 1 or into equation 2. I'm going to plug it into equation 1. This seems to be a little bit simple compared to equation 1. I'm sorry, equation 2. So when you plug k equal to approximately 0.9613, this is equal to 400 equals P naught e raised to the power of 2 times of k, which is 2 times of 0.9163. And so we can determine the value of P naught from this equation. We divide by this quantity, that is e raised to the power of 2 times of 0.9163. So therefore, P naught equals 400 over e raised to the power of 2 times of 0.9163. We can plug this expression into the calculator, and when we do that, we get the approximate value of P naught, and this is approximately equal to 64. So we have determined the initial size of the culture, which is 64. Let's answer question 3. So here we have to write the expression for the number of bacteria after t hours, which is basically we have to write the function p of t. So since we know that our model is p of t, this equals p naught e raised to the power of kt. So all that we have to do is we have to replace the value of k as well as the value of P naught, which is the initial size of the bacteria, into this model. So when we do that, we get the expression for the number of bacteria, that is P of t. This equals P naught equals 64, and e raised to the power of k times of k is 0.9163. So 0.9163 times of t. So this is the expression which is used to determine the number of bacteria after T hours. Question 4 asks us to determine the number of cells after 4 hours. So basically, this is when T equal to 4, we have to determine P of T. So we have to replace T by 4 into this model. So I'm going to replace T by 4. So therefore, this becomes P of 4, and this equals 64 times of e raised to the power of 0.9163 times of 4. Replace t by 4. So we can plug this into the calculator. That is, we just have to multiply these two quantities first, and exponent e by this quantity and multiply by 64. So when we do that, we get approximately as 2500. So this is the number of cells after 4 hours. In question 5, we have to determine the time it takes for the population to reach this quantity. That is, this is 1 million. So let's see how to determine the time. We can use this population model. So let me first copy this population model. P of t equals 64 times of e raised to the power of 0.9163 times of t. And here we have to replace P of t by 1 million, or we can represent this simply as 10 power 6, and this equals 64 times of e raised to the power of 0.9163 times of t. First, I'm going to divide by 64. So this 64 will get cancelled over here. So therefore, in the next step, we see that we will have 10 power 6 by 64 here on the left side, and on the right side we will have e raised to the power of 0.9163 times of t. So to determine the value of t, we have to take a logarithm on both sides. So let me take a natural logarithm. That is, take a natural logarithm on both sides. And this means we will have natural logarithm of 10 raised to the power of 6 divided by 64. Sorry, this is 64. And this equals natural logarithm of e raised to the power of 0.9163 times of t. Let me put this inside this brackets. And as we have seen in problem 1, we know that we can bring this power in front according to the power rule of natural logarithms. So therefore this power is 0.9163 times of t, and then multiplied with natural logarithm of e. We will have natural logarithm of e. We know the natural logarithm of e is 1, so we can simply ignore, because 1 times of this quantity is, we're going to left with this quantity. And on the left side we have natural logarithm of 10 power 6 divided by 64. So now we can determine the value of t when we divide both sides by this quantity 0.9163. And let me rearrange so that I have t on the left side. So therefore this is going to be natural logarithm of 10 power 6 divided by 64 divided by 0.9163. So we can plug this expression into the calculator. So make sure that you plug it as properly as possible. You have to first plug in this expression 10 power 6 over 64, and then apply natural logarithm to this, and finally over 0.9163. So when we plug this into the calculator, we get the approximate value of t, and this equals, this is approximately equal to 10.5 hours. Since time is measured in hours, we put the unit as 10.5 hours. So this is the time, that is, it takes about 10.5 hours for the count or the number of bacteria to reach 1 million. I just figured out that instead of 10.5, we can give this in 2 decimal places as 10.54. So this is considered to be a good approximation rather than 10.5. So let's change this to 10.54 hours. So T is approximately 10.454 hours, so that the population will reach 1 million.